Welcome to Inside the Item channel. Residential condensing boilers provide efficient heating. They operate by condensing water vapor from exhaust gases. The boiler's exterior houses a complex system. It includes a heat exchanger, burner, and controls. These components work together to achieve high efficiency. Condensing boilers reduce energy consumption. They achieve this by capturing heat from flue gases, which would otherwise be lost. This process increases efficiency by up to 90%. The heat exchanger is a critical component. It transfers heat from the burner to the water. This process occurs through a series of tubes and fins, maximizing heat transfer. Condensing boilers also reduce emissions. They produce fewer pollutants, such as nitrogen oxides and carbon monoxide. This is due to the lower temperatures at which they operate. In residential settings, condensing boilers offer significant benefits. They provide reliable, efficient heating while minimizing environmental impact. A properly installed boiler can last up to 15 years. Development of condensing boilers began in the 1980 seconds. Early models were largely inefficient and unreliable. They paved the way for modern designs. In the 1990 seconds, advancements in materials led to improved heat exchanger designs. This increased efficiency by 20% and reduced manufacturing costs. By the early 2000 seconds, electronic controls became standard. These controls optimize burner performance, reducing emissions by 30% and improving safety. In 2005, the introduction of stainless steel heat exchangers increased durability. This extended the boiler's lifespan by 5 years and reduced maintenance costs. Modern condensing boilers now achieve efficiencies of up to 98%. This is due to advanced burner designs and improved insulation, reducing heat loss by 10%. Today, condensing boilers are a staple of residential heating. With ongoing research, they continue to evolve, providing even greater efficiency and reduced environmental impact. A condensing boiler's exterior is designed to withstand various environmental conditions. The boiler's dimensions and insulation ensure minimal heat loss, typically around 2–5%. This efficient design allows for optimal performance in residential settings. The internal components of a condensing boiler include a primary heat exchanger, a secondary heat exchanger, and a burner. These components work together to facilitate the condensation process, with the primary heat exchanger accounting for approximately 70% of the total heat transfer. The condensation process occurs when the temperature of the flue gases drops below the dew point, typically around 55 C. This causes the water vapor to condense into liquid water, releasing latent heat, which is then transferred to the heating system, increasing efficiency by up to 12%. Heat exchangers in a condensing boiler are designed to maximize heat transfer, with the primary heat exchanger operating at a temperature of around 80 C. The secondary heat exchanger, operating at a lower temperature, facilitates the condensation process with a heat transfer coefficient of approximately 0.05 watts/chem/K. The burner in a condensing boiler is designed to operate at a low nitrogen oxide emission level, typically below 40 milligrams per kilowatt hours. This is achieved through the use of advanced combustion technology, which ensures a stable and efficient flame, with a combustion efficiency of around 95%. The condensing boiler's overall efficiency is determined by the combined performance of its components, with a typical seasonal efficiency of around 92%. The boiler's ability to condense water vapor from the flue gases, combined with its advanced heat exchanger design, results in significant energy savings and reduced emissions, making it an attractive option for residential heating systems. The condensing boiler's heat exchanger is designed to withstand high temperatures, up to 100 C. The heat exchanger's surface area is typically around 2 square meters, allowing for efficient heat transfer. Its compact design enables easy installation in residential settings. The burner in a condensing boiler operates at a precise air-to-fuel ratio, typically around 10:1. This ensures complete combustion, reducing emissions and improving efficiency. The burner's ignition system is designed to provide a reliable and consistent flame. The controls in a condensing boiler regulate the burner's operation, maintaining a consistent temperature, typically around 80 C. The controls also monitor the boiler's performance, adjusting the air-to-fuel ratio as needed to optimize efficiency. This results in a reduction of energy consumption by up to 15%. The primary heat exchanger in a condensing boiler is designed to transfer heat from the burner to the water, operating at a temperature difference of up to 20 C. The heat exchanger's tubes are typically made of stainless steel, ensuring durability and resistance to corrosion. This design enables the boiler to achieve an efficiency of up to 95%. The condensate trap in a condensing boiler is designed to collect and remove condensate, typically at a rate of 1 to 2 liters per hour. The trap's design ensures that the condensate is removed efficiently, preventing blockages and maintaining the boiler's performance. This results in a reduction of maintenance costs by up to 10%. Condensing boilers' overall design ensures efficient and reliable operation. The components work together to deliver a high level of efficiency, reducing energy consumption and emissions. This makes condensing boilers an attractive option for residential heating systems, with a potential energy saving of up to 20%. The heat exchanger is the core component of a condensing boiler, responsible for transferring heat from the burner to the water. It operates at a temperature of up to 90 C, with a heat transfer rate of approximately 20 kilowatts. The heat exchanger's design enables efficient heat transfer, resulting in a boiler efficiency of up to 98%. The heat exchanger's internal layout consists of a series of tubes and fins with a total surface area of approximately 1.5 square meters. The tubes are typically made of stainless steel, ensuring durability and resistance to corrosion. The heat exchanger's design enables a heat transfer coefficient of around 0.1 watts MUSH-K. The primary heat exchanger operates at a temperature difference of up to 25 C, transferring heat from the burner to the water. The heat exchanger's tubes are designed to maximize heat transfer, with a typical tube diameter of 20 millimeters and a tube length of 1.2 meters. This results in a heat transfer rate of approximately 15 kilowatts. The secondary heat exchanger operates at a lower temperature, facilitating the condensation process. It has a surface area of approximately 0.5 square meters, with a heat transfer coefficient of around 0.05 watts/kmK. The secondary heat exchanger is designed to transfer heat from the flue gases to the condensate, resulting in a condensation rate of approximately 1 liter per hour. The heat exchanger's materials are selected for their high thermal conductivity and resistance to corrosion. The tubes are typically made of stainless steel, with a thermal conductivity of around 15 watts/K. The heat exchanger's design enables efficient heat transfer, resulting in a boiler efficiency of up to 95%. The heat exchanger is a critical component of a condensing boiler, enabling efficient heat transfer and high boiler efficiency. It operates in conjunction with the burner and controls to provide reliable heating, with a typical seasonal efficiency of around 92%. Durable stainless steel construction helps it withstand years of daily operation. Combustion process in a condensing boiler begins with the ignition of fuel, typically natural gas or propane. The fuel is mixed with air and the mixture is ignited, producing a flame. This flame heats the water, producing steam, which is then used for heating. The boiler's combustion chamber is designed to ensure complete combustion, with a typical combustion efficiency of around 95%. The combustion process involves the reaction of fuel with oxygen, producing carbon dioxide and water vapor. The air supply is critical, with a typical air-to-fuel ratio of around 10 to 1. This ensures complete combustion, reducing emissions and improving efficiency. The burner's design enables a stable and efficient flame with a combustion temperature of up to 1800 C. The combustion process also produces nitrogen oxides, which are harmful pollutants. To reduce these emissions, condensing boilers use advanced burner technology, such as low NOx burners. These burners operate at a lower temperature, typically around 1500 C, reducing nitrogen oxide emissions by up to 70%. The condensation process is critical in reducing emissions. As the flue gases cool, the water vapor condenses, releasing latent heat. This heat is then transferred to the heating system, increasing efficiency. The condensation process reduces emissions by up to 20%, making condensing boilers a more environmentally friendly option. The emissions reduction in condensing boilers is also achieved through the use of advanced materials and designs. The heat exchanger is designed to maximize heat transfer, while the burner is designed to minimize emissions. The boiler's controls also play a critical role, regulating the combustion process and optimizing efficiency. This results in a reduction of energy consumption by up to 15%.
In conclusion, the combustion process in a condensing boiler involves the reaction of fuel with oxygen, producing heat and emissions. Through advanced burner technology and condensation, those emissions are significantly reduced, making this design a more environmentally friendly option for home heating.
Condensate management is crucial in condensing boilers. The condensate forms as the flue gases cool, and its proper disposal is essential to maintain boiler efficiency and prevent damage. The condensate has a typical pH level of 3.5, making it acidic and requiring careful handling.
Condensate trap is a critical component in condensate management. It collects and removes condensate from the boiler, typically at a rate of 1 to 2 liters per hour. The trap's design ensures that the condensate is removed efficiently, preventing blockages and maintaining the boiler's performance.
The condensate drainage system is designed to handle the acidic condensate. It typically consists of a drainage pipe, a trap, and a ventilation pipe, ensuring that the condensate is safely disposed of without causing damage to the surrounding environment or the boiler itself. The drainage pipe is usually made of PVC or ABS with a diameter of 20-30 millimeters. Proper installation of the condensate drainage system is essential. The drainage pipe should be installed with a minimum slope of 1 to 100, ensuring that the condensate flows freely and does not accumulate in the pipe.
The trap should be installed at the lowest point of the drainage system, with a ventilation pipe providing a means of ventilation and preventing siphoning. Regular maintenance of the condensate drainage system is necessary to prevent blockages and ensure proper function. The trap should be checked and cleaned regularly, typically every 6 to 12 months, to remove any debris or sediment that may have accumulated. The drainage pipe should also be inspected for any signs of damage or corrosion.
In summary, condensate management and drainage are critical aspects of condensing boiler operation. Proper design, installation, and maintenance of the condensate drainage system ensure safe and efficient disposal of the condensate, maintaining boiler efficiency and preventing damage. The condensate drainage system is a vital component of the boiler, and its proper function is essential for reliable and efficient heating.
The control panel regulates and monitors the boiler's operation. It typically includes a user interface, sensors, and control circuits, ensuring safe and efficient operation with a response time of around 1 to 2 seconds.
The electronic controls in a condensing boiler monitor and adjust the boiler's operation in real time. They include temperature sensors, pressure sensors, and flow sensors, which provide accurate readings, typically with an accuracy of 1%. The controls use this data to optimize the boiler's performance, reducing energy consumption by up to 10%.
Temperature sensors in a condensing boiler monitor the temperature of the boiler's water and flue gases. They provide accurate readings, typically with an accuracy of 0.5 C, which are used to adjust the boiler's operation and prevent overheating, with a maximum temperature limit of 100 C.
The safety features of a condensing boiler include overheat protection, which prevents the boiler from operating above a safe temperature, typically 110 C. This feature is critical in preventing damage to the boiler and ensuring safe operation, with a response time of around 1 to 2 seconds.
The control panel also includes a fault detection system, which monitors the boiler's operation and detects any faults or anomalies. It provides alerts and notifications, typically through a display or warning lights, to indicate any issues, with a typical response time of around 1 to 2 seconds.
In summary, the controls and safety features of a condensing boiler work together to ensure safe and efficient operation. The control panel regulates and monitors the system, while the safety features prevent overheating and catch faults before they become problems.
Proper installation is crucial for efficient and safe operation. The boiler should be installed in a well-ventilated area with a minimum clearance of 300 millimeters from any combustible materials, giving service engineers easy access for future maintenance. The installation process involves connecting the boiler to the heating system, including pipes and vents. The pipes should be insulated to minimize heat loss, with a typical insulation thickness of 20 millimeters. The vents should be installed to ensure proper airflow, with a minimum diameter of 100 millimeters.
Regular maintenance is essential to ensure the boiler operates efficiently and safely. The boiler should be serviced annually, including cleaning the heat exchanger and checking the combustion chamber, with a typical maintenance cost of $100 to $200. This helps to prevent issues and maintain efficiency.
Troubleshooting common issues such as faulty ignition or blocked vents can be done using the boiler's control panel and diagnostic tools. The control panel provides error codes and alerts, with a typical response time of 1 to 2 seconds to help identify and resolve issues quickly.
In the event of a fault, the boiler's safety features will activate to prevent damage or injury. These features include overheat protection and fault detection, with a typical response time of 1 to 2 seconds, which alert the user to potential issues and provide guidance on resolving them.
By following proper installation, maintenance, and troubleshooting procedures, a condensing boiler can provide efficient and safe heating for up to 15 years, with a potential energy saving of up to 20%. Regular servicing and maintenance are crucial to ensuring the boiler operates at its best.
Condensing boilers have revolutionized residential heating, offering unparalleled efficiency and reduced emissions. With a typical efficiency of up to 98%, they have become the go-to choice for environmentally conscious homeowners.
The internal components of a condensing boiler work in harmony to achieve high efficiency, with the heat exchanger, burner, and controls playing critical roles. The heat exchanger, for example, can transfer heat at a rate of up to 20 kilowatts. Advances in materials and design have enabled condensing boilers to operate at lower temperatures, reducing emissions and improving efficiency. For instance, the use of stainless steel heat exchangers has increased durability and resistance to corrosion.
Future developments in condensing boiler technology are expected to focus on integration with renewable energy systems, such as solar and heat pumps. This integration can increase overall efficiency by up to 10% and reduce emissions even further.
Increased efficiency and reduced emissions will be achieved through the use of advanced burner technology and improved insulation. For example, the use of low NOx burners can reduce nitrogen oxide emissions by up to 70%.
As the demand for efficient and environmentally friendly heating solutions continues to grow, condensing boilers will remain at the forefront of residential heating technology. Thanks for watching. If you haven't subscribed yet, hit that subscribe button.